Hi everybody. Welcome to the lesson on sampling distributions and their applications. This is sort of a couple of sections from Chapter 7 lumped together into one. We're kind of hitting the highlights of Chapter 7 here. I don't want to spend too much time in Chapter 7 because I want to hurry up and get to the inferential statistics part of the course. All right, so let's start by reviewing a couple of things about random variables. First of all, random variables have values that differ based on the particular element, particular person, particular whatever it is that the population is composed of, based on a particular one of those that are selected. And we said every random variable has a distribution, and we've looked at the normal distribution and we've looked at some discrete distributions. There are lots of other ones, but we haven't looked at those. Every random variable also has a mean, and we've said that that was mu because random variables describe a population, and we said that it always has a standard deviation, which is sigma. Again, because it describes the population. If you don't remember what those symbols stand for, this is a really, really good time to go look for them, make your list, and keep those handy. So all of the probability problems that we've looked at so far have been looking at distributions of individuals. We looked at, in the last lesson, individual tax refunds. So that was a distribution of the amount of tax refunds that individuals would get. Okay, all of those were individuals. Well, in this section, we're going to look at distributions not of individuals, but of sample means. All right, so X bar, the sample mean, varies from sample to sample. If I take a different sample, I get a different sample mean. That makes it a random variable. Since it's a random variable, the sample mean itself has a distribution shape, a mean, and a standard deviation. So, just again, we've got, if we pick a different sample mean, we get a different value. If we did that over and over and over again and did a histogram of those values, that's what we're looking at, is the distribution of what those are. So some of those ranges of values for X bar are going to be more likely than others. And that's what we're looking at here. So when you look at the distribution of a statistic, that's called a sampling distribution. A statistic, I believe we talked about, is a characteristic of a sample, like a sample mean, or a sample standard deviation, or a sample proportion. All right? So anytime we're looking at the distribution of a statistic, that's called a sampling distribution. We're only going to look at one of those, and that's the distribution of the sample mean. So, the central limit theorem is important to us because it tells us what is the distribution, the mean, and the standard deviation of that sample mean. Okay? So, imagine this at the outset. We're taking a sample from a population, and I'll type this out here. So, we're taking a sample from a population with a mean of mu, which I'll have to fill in a minute, because this won't type mu for me, and a standard deviation of sigma. Okay, this distribution, it has a distribution. That distribution may be normal or it may not be normal. It may be discrete or it may be continuous. Okay, so this is mu and this is sigma. So what this tells us is, if I were to take repeated samples from this population, the mean of all of those possible sample means is the population mean. What this tells us is that the sample mean should be centered right around the population mean. So that shouldn't be surprising. If we take a sample and we calculate the mean, that should be pretty close to the population mean. Okay, so that's good. This symbol is read as mu sub x bar. All right, so this is mu sub, like a subscript, x bar. Okay, so again, this is just telling us that the mean of all of the possible sample means is the population mean. The standard deviation of all of the possible sample means is not the same as sigma. And if you think about it this way. When we look at the distribution of x bars, every x bar represents the center of that sample. So which one would you expect to be more spread out? A sample of individuals or a sample of middles? And I believe the answer pretty clearly should be that the individuals are going to be more spread out, because it's much more likely that you'd have one unusual element than it would be to have a whole bunch of them together in one sample. So this is smaller than the original population by a factor of the square root of n. And this is read as sigma sub x bar. All right? So that's the first two parts of the central limit theorem. The third part, and this is really powerful for us, it may not sound like it at first, but the distribution of the sample means is normal. So it follows a normal distribution, provided one of these two things is true. Provided the sample is large, and as long as you have about 30 or more, that's considered large. And I'll explain to you why here in a couple of weeks. Or if you're told that the original data follows a normal distribution. For our purposes, you probably need to be told that. Or you might look at a histogram. Anyway, so x bar follows a normal distribution provided you know one of these two things. Anytime you know that the sample is large, then yes, you can say that the sample mean follows a normal distribution. Or anytime you're told that the original distribution was normal, you can say that the sample mean follows a normal distribution. As long as you have one of those, you're fine. So now let's look at an example. Suppose we take a sample of 15 new small businesses. and we're going to calculate the mean profit that they get in the first year. Can we conclude, based on what we've got here, that the sample mean follows a normal distribution? Well, if we look back at our two conditions here, the first question is the sample large? And we're looking for 30 or more, and we don't have that. So now let's look and see if the original data followed a normal distribution. Well, we're not told that either. So the answer is no, because neither one of our conditions is met, because n, the sample size, is small, and we're not told the original population followed a normal distribution. Okay, so that's that one. Now let's look and see, what if we collected some more data? When we say, okay, now we're going to take a sample of 50 new small businesses. Can we conclude the sample mean follows a normal distribution? Well, in this case, yes. Because even though we're still not told that the original distribution was normal, we have a large enough sample size here. All right, so let's keep going. Let's see now what we can do with that information. So if we know that the sample mean follows a normal distribution, we can then find probabilities relating to the normal distribution, or relating to the sample mean. So in this next problem, we're asked to find the probability that a sample mean is in a certain range. And I want to add this word on average here. So the first thing we should do here is, and we already up here verified that, that the sample mean follows a normal distribution. Let's figure out what our mu sub x bar and sigma sub x bar are. So mu sub x bar is going to be just the population mean. So this first sentence here is describing the population. Okay, for all new small businesses, this is the mean and the standard deviation. So here mu is going to be 43,000. And we're also going to need sigma sub x bar. That doesn't look like x bar. That's a little better. And that is going to be sigma over the square root of n. And they tell us that sigma is 31,000. And that's going to be divided by the square root of the sample size. So we need to do 31,000 divided by the square root of 50. And remember, in this class, all of our computations need to be done in Excel. So we're not using a calculator for anything. All right. And let's keep plenty of decimal places here. Let's round these to at least 3 decimal places. This is 4384.062. And the reason is, anytime you're doing computations with a number that has been rounded, you get compounding round-off error. So you want to be really careful with that. And as business majors, that's the kind of thing you should definitely be aware of. All right, so now let's find the probability that the sample of 50 new businesses will have a profit rather than a loss. Meaning, in other words, what's the probability that the sample mean will be greater than 0? Right? So, here's what I need to tell you. If you remember when we were doing the normal distribution, the plain old normal distribution, when we were converting from x to z, we subtracted mu and divided by sigma. That's because we were looking at individuals, and those were x, and so we subtracted the mean of the x's and divided by the standard deviation of the x's. Well, now we want to convert to z again, but we want to convert from x bar to z. Well, now we're going to do almost exactly the same thing, except now we're subtracting the mean of the x bars, and we are dividing by the standard deviation of the x bars. So this is almost exactly the same process we went through when we were doing, in the last section we were doing the normal distribution. It's just that here we now have sigma sub x bar and mu sub x bar instead of sigma and mu. Okay? So, let's convert to z, just like we did before. And 0 goes on the top here, because that's what our theorized x bar was, minus mu sub x bar, so 43,000. And we're going to divide by sigma sub x bar, which we found to be 4384.062. So now this is going to be the probability that z is greater than, and let's figure out what this is in Excel. So, and I'm going to put this in just the way you would. So 0 minus 43,000. Yes, I know in this case that's just negative 43,000, but I want to show you the way you would do it. Divided by this value that we calculated previously. And we get negative 9.808. So now at this point we just have to find, just like we've been doing, the probability relating to a z. Well, I'm sure you remember by now, because we've gotten plenty of practice with it, how to do the probability that z is greater than. If you've forgotten, I would encourage you to go back and look at that part of the video from 2 classes ago. And this is going to be, so 1 minus norm s dist, parentheses, negative 9.808 0.808 true. So 1 minus norm S dist. This value means if we just click on that value, it means we don't have to worry about rounding. True, and we get 1. And that's not exactly 1, it's just 1 rounded to a whole lot of decimal places. All right, so this tells us that in our sample of 50, it's almost guaranteed that that sample of 50 is going to have a profit their first year. All right, let's move on to the next example. So in this example, and this is the one we saw last class, federal tax refunds of people who are single with no dependents, those follow a normal distribution with a mean of $800 and a standard deviation of $120. So the first question here is, what is the probability a randomly selected single person with no dependents has a tax refund greater than $850? I put this question on here so that you can see how this question differs from some of the other ones. If you look at this question up here, in the last problem we said, what's the probability a sample of 50 will have a profit rather than a loss? So this one is asking for the probability relating to the sample mean. Okay, so this one is the sample mean. This one down here, though, says what's the probability that a randomly selected. So this is just, I don't know what happened with that line. My mouse pen goes a little nuts sometimes. So this one, again, is the probability that a randomly selected single person. So this is just one individual. So this is the probability, not of x bar, but of x. And again, the difference here is whether they're asking about one randomly selected individual versus a mean of a bunch of randomly selected individuals. Okay, so this one is just like what we were doing in the last section. So this is probability that x is greater than 850. And we're going to convert that to z. So 850 minus the mean, which is 800, divided by sigma, which is 120. So, over in Excel, 850 minus 800 over 120 gives us 0.4167. And this is another greater than one, so we're going to do 1 minus norm S dist, that 0.417, comma true. And let's see what we get. Norm S dist And we're clicking on that cell, so we don't have to worry about rounding, comma, true. And so our answer there is 0.33. We can round to 3 decimal places, 0.338. So now let's look at part B. Part B says if we sample 25 of the people from this population up here, can we say the sample mean follows a normal distribution? And here the answer is yes, because even though we only have 25 people, we're told that the original population followed a normal distribution. So yes, because the original population followed a normal distribution. All right? So now the next part says, well, what is the mean of that sampling distribution? And that symbol is mu sub x bar, and that equals the population mean, which they tell us in the problem is 800. Next, what is the standard deviation of the sampling distribution? In other words, what is sigma sub x bar? Well, we know, because we've seen it before in the notes a little bit, that is sigma over the square root of n, which is, we know that sigma, the standard deviation, is 120. Divided by the square root of the sample size. And we know that the sample size here is 25. So we'll come over here and we'll do 120 over the square root of 25. And that comes out to be 24. So in part E, find the probability that the mean tax refund, so x bar, will be less than 850. So this is going to be the probability that z is less than, we just convert 850 to z, we subtract the mean of the x bars, so 800, and we divide by the standard deviation of the x bars, and we get 24. So this is the probability that z is less than 850 minus 800 over that 24, and we get 2.0833. And that's less than, so that's just going to be norm as dist .083 true. And let's see what we get. and we get 0.9184. So it looks like most of our samples of 25 will have a mean less than $850. So let's just do a little recap. In the original population that we're sampling, its random variable is called X. Whereas in the distribution of X bars, this is the sampling distribution, its random variable is X bar. The mean of the original population is mu. The mean of the distribution of X bars is mu sub X bar, which is still mu. The standard deviation of the original population was sigma, whereas the standard deviation of X bars is sigma sub X bar, which is sigma, that sigma, over the square root of n. The original population being sampled may or may not be normal, but we know that X bar follows a normal distribution if either we have a large sample size or we know that the original population being sampled was normal. In our original population, if it followed a normal distribution, we'd convert to z using x minus mu over sigma, whereas for x bar, we convert to z using x bar minus mu sub x bar over sigma sub x bar. And that comes out to be, I don't know if you can see that being so small. We know that mu sub x bar is mu, so that's just mu, over sigma sub x bar is sigma over the square root of n. All right, one more thing, and that's, who cares? Why does it matter if we calculate probabilities relating to x bar? The answer is that sampling distributions bridge. This is the bridge between probability and statistics. This is what allows us to do inferential statistics. So in the coming weeks, we're going to use this as the basis of being able to find an interval that we think is likely to contain the population mean. And we're going to do that by taking this formula and sort of working backwards with it. And this is a statistical inference, finding an interval that's likely to contain the population mean. And then the other kind of inference we're going to do is we're going to be able to look at a hypothesized value and say, does it seem reasonable to think that our population mean is that value? Or is it less than that? Or is it greater than that? And that's hypothesis testing. And between those two things, we're going to spend most of the rest of the course doing that. And the central limit theorem and other theorems like it is the only reason we can do those things. All right, so that's it for this lesson. And as always, please let me know if you have any questions.